Hello, welcome back to Kiersti's virtual classroom. Today we're talking about geologic time and radiometric dating. So let's get right into it. So, how old is the Earth? We've kind of alluded to some of this before with other topics, but the Earth is 4.6 billion years old, which sounds like a lot, and it is a lot. Humans have only been here for about 200,000 of those 4.6 billion years. So if you do the math, that's a very, very small percentage of time that we've actually been around. And the Earth is broken up into different segments depending on what happened during those times, when there are major extinction events or major evolution events. So that is the geologic timescale, which you kind of see here with this little spiral. Another way to look at it, which you have seen before, is the geologic timescale, which is constantly revised based on what scientists and geologists discover. So right now we are in the Quaternary period of time, and the timescale is broken up into eons, eras, periods, epochs, and ages. And like I said, those are all dependent on extinction events, evolution events, and different things that they've seen in the rock and fossil record. So here's another look at it. To give you some perspective, the Precambrian period is almost 90% of Earth's history. So most of what you see after the Precambrian is most of life's evolution, and that takes up the, spatially larger portion of the timescale, even though as far as number of years go, the Precambrian, where not a lot happened, takes up the most time. So how do we know how old the rocks and fossils are and put them on that geologic timescale? So we use something called relative age dating and absolute age dating. So usually in the field, it's really easy to use relative age dating. You can look at a rock unit, you can look at fossils that you see in rock units, and you can kind of surmise what came at what order. So this is putting things in order based on what you're seeing in the field, usually. Absolute age dating is a little bit more tricky. It requires sampling, but this is where we can actually put things in chronological order and give a numeric value to the age of that rock or fossil. So in this picture here, it shows you that it's pointing to some rock unit and saying that it's 120 plus or minus 5 million years old. So that's an absolute age of that rock, whereas on the left here, the relative age is just that this one is younger than the one below it. And we'll talk about different principles that help you tell in the field what's older than what. So those are called geologic principles. And these are the principles that help tell us how old different rocks are in relation to other rocks. It also applies to the fossils. So if you have a fossil in a particular unit, you know that it's around the same age as that unit. Okay, so the first conceptual principle that we're going to talk about is the principle of uniformitarianism. This says that the present is the key to the past. So here, geologists look at things that they can see in the field, and they can make assumptions as to what happened in the past. So we take our geology brains, turn them on, and say, okay, I see ripples here. So we've talked about ripple marks before. That means that there must have been flowing water or wind here at some point in time, right? Okay, so this is something that geologists use not only for dating methods, but trying to decipher anything that happened previously in Earth's history. Okay, so another one is the principle of faunal succession. So this says that a group of fossil plants and animals have followed one another in a definite, discernible order. So certain fossil assemblages characterize a specific time. So we talked about index fossils. So trilobites here are a good index fossil. They lived over a very short period of time, but they were found globally. So if you're looking at a rock that has a trilobite in it, then you can already surmise about what age it is. So for instance, this trilobite in this rock indicates that this rock is somewhere between Cambrian and late Permian in age. Okay, so those were the conceptual. Now we're going to talk about the geometric. So this has to do with observing things in the field and trying to discern them in a particular order. So the first one here is that, we've talked about this before, sedimentary rocks are laid out in horizontal layers unless something else has happened to them since their deposition. Everything, as far as sediments go, will line up in horizontal fashion, and they will just build up from there. So you'll see deposits of sedimentary rocks in horizontal layers. So this is called the principle of original horizontality. If it's no longer horizontal, then something has happened to it, and we can surmise that that's something that happened to it, like a tilting event, or it folded. That happened after its deposition. So the rock is older than the event. Okay? So the principle of superposition is another one that we use a lot. I've already kind of alluded to it. Anything that is on the bottom of a sequence of layers is going to be your oldest. And as you move up, it gets younger and younger. So it's similar to like a basket of laundry. So at the beginning of the week, when your laundry basket is hopefully empty, you put your Monday clothes at the bottom. And then you put your Tuesday, and then Wednesday, and then Thursday, and then Friday. And by the time it's time to do laundry, you know that the oldest clothes that you wore first are at the bottom. So the oldest is at the bottom, the youngest is at the top. It's the same thing with rock units. The oldest gets deposited first, and then the next oldest, and all the way to the top where you'll see your youngest sediments. So this is the principle of superposition. Now, the principle of cross-cutting relationships helps us distinguish when a fault cuts through an area, or if we have a igneous intrusion, which we also call dikes, we can tell whether that is older or younger than the unit it is crossing. So, in essence, the cutter, which is this dike here, is younger than the cuttee, which is what it's cutting through. So all of these layers here are older than whatever is cutting through it, whether it's this dike, an igneous intrusion of some sort, or it's a fault. Okay, and we'll practice that a little bit more. But if it cuts through the layer, then the layer had to be there before it could cut through it. Okay. The age of inclusions is another good one. If we have something called an inclusion or a xenolith, which is basically a rock fragment that has been enveloped into another rock. So here we have an intrusion piece, and then another rock that kind of engulfed that piece. So as we know, weathering and erosion occurs, and bits and fragments of rocks break off their original rock unit, and they can be incorporated into other rocks as those form. If that happens, that is our intrusion or our xenolith within this bigger rock unit. And if we have an inclusion, then we know that that inclusion had to exist before the rest of the rock. So the inclusion is older than the rock that it is in. So this is similar to like baking chocolate chip cookies. You can't bake the chocolate chip cookies if the chocolate chips don't already exist, right? You don't make those after you make the chocolate chip cookies. So the chocolate chip cookies exist, or sorry, the chocolate chips exist. You include those into your chocolate chip cookie, and now you have basically an example of an inclusion. So the chocolate chip is older than the cookie. All right, another one is lateral continuity. So as rocks are weathered, especially by rivers, you will see this valley form. Sometimes it's a V-shaped valley, sometimes you end up with some more U-shaped valleys. And those valleys separate rock units, but that doesn't mean that the rock units on either side are different. So what we see in something like the Grand Canyon is that these rock units here on the right are very similar in age, color, and rock type to those on the left side of this little canyon here. And so you would surmise, based on the principle of lateral continuity, that these are probably the same rock unit. And so the principle of lateral continuity says that sediments are not deposited and then truncated. So this would be an example of truncation, where you have this thick ending to a sediment. They are laterally continuous sheets. So they deposit as big sheets of sediment, and then they further get eroded into, and it looks like they're truncated. But really, at the end of a deposition, you're going to see a thinning out of material. Okay, so you're not going to see this large truncation just because there is a canyon here. So that canyon is just separating the rock units even though they're the same. So you can see the same layers on both sides of a canyon. All right, then we get into something called an unconformity. So an unconformity is an erosion surface. So this is a gap in the rock record. This is where we don't have continuous deposition of sediments. Okay, so we have these classified based on their interactions and whether you're looking at tilted layers or non-tilted layers. So we've got nonconformities, disconformities, and angular unconformities. So we'll go through each of those individually and talk about them. So the first one here is a nonconformity. This happens between an igneous or metamorphic rock that's overlain by a younger sedimentary rock. And so you get this unconformable surface where it had eroded this schist and gneiss, and then after the erosion occurred, some sandstone was deposited on top. Here's a little cartoon evaluation of that. So you have some original deposition, you had some erosion all the way to the bottom of this little dotted line here. That erosion surface was then covered with sediments, and it formed the nonconformity. The way that I help students remember this one is that they don't conform. So you say nonconformity, they're not the same rock type. So here it's either igneous and sedimentary or metamorphic and sedimentary. So it's not the same rock type between the two. So your gap in the rock record is a nonconformity. They don't conform to each other. All right, and then another one is a disconformity. So this is between two sedimentary rock layers. So the same type of thing happens. You have original material that is then eroded into, that it creates an erosion surface, and then you have more deposition on top of that, and that forms your disconformity. But the deposition has to be another sedimentary rock. Okay, it doesn't have to be the same type of sedimentary rock. It can be a limestone and a sandstone, or a siltstone and a conglomerate. So this here looks like it's a sandstone and then a conglomerate on top of it here. So it doesn't have to be sandstone, sandstone. They just both have to be sedimentary rocks to be a disconformity. So the other way that I help students remember this one is that the sedimentary rocks think they're cooler than everybody else, so they diss all the other rock types. It's a disconformity. It's kind of a silly way to remember it, but you probably won't forget it now. All right, and then the last one here is an angular unconformity. So this occurs when you have angled beds or folded beds overlain by horizontal beds. So here the evolution of an angular conformity would be deposition of different layers. They get deformed in some manner, so here they're folded. Then they are eroded, and then more deposition comes on top. And that deposition is of course horizontal because, as we discussed, sedimentary rocks are laid down horizontally initially. Okay, so you see something like this. Here we have some angled beds, and it's capped with a horizontal layer. So the difference between there is an angular unconformity. All right, so these slides, we're going to talk about a few different sketches, and we're going to see if we can figure out what order they came in. This is something that you're going to do in lab, and you will likely do on the exam. So this will go step by step. Normally we would do this in class, and you'd kind of participate and yell out. Feel free to pause the video and do it yourself if you would like. It definitely helps. But we will go through kind of at a slower pace as if I was actually asking you the questions. Okay, so this is the first cartoon or diagram that we will go through. So there are 17 steps total, and there's a couple of extra ones that I've labeled here. So if you want to pause the video, now would be a good time and try to figure out if you can do it on your own. Otherwise, you can keep going and watching. Okay, so the oldest one here is going to be, you're going to look at the bottom. So you're going to want to start at the bottom here because of the principle of superposition. The oldest should be towards the bottom. You know that there's a tilting event of some layers, but those layers have to be there before they can be tilted. So the oldest is likely A. And then on top of A would be B. Then we'll see C. D, and then E. Okay, the next thing that's really important is to try to figure out when F, G, or L showed up. One other important thing to notice is that there's two different tilting events. These beds here are tilted at a different angle than these ones here. So they are two different tilting events. So we're going to treat the bottom here separate from the top. Okay. So L goes through all of these layers with the exception of N. So L must be younger than all of these layers. So we're not going to worry about that one right now. Then we have F and G. One thing that you'll notice is that all of these layers in here, other than when you get to H, all of these are offset by this fault G. Okay? If they're offset by this fault G, but you can't see the rest of the faults, then it must be older than this intrusion here that's kind of covering it up. Okay? So the next oldest must be G. And then we have F. Oh, I'm sorry, and then we have the tilting event, and then F. F or the tilting event could be older or younger. It's really hard to tell because you don't see any tilting evidence in F, but that doesn't mean that it wasn't tilted and you're not really seeing the tilt of it. Okay, so for now we're just going to say the tilting event and then F. And then our unconformities. So here is our unconformity. So unconformities are defined by either squiggly lines in diagrams, or this one's kind of squiggly and very dark lined. So that would be our unconformity. And then the next layer we're going to do is going to be starting from the bottom again. So we've already got all of these guys down here. So our next one would be H, and then I, J, K. Now we've already talked about L being through all of these layers. L also doesn't look like it's tilted very much because this is kind of horizontal here. So I would imagine that the tilting event came before L. So we'd have our tilting event P, and then we would see L, and then we have our last unconformity here, and then the last layer is that one there on top, N. Okay, so hopefully that one was okay. We are going to move on and do a couple more. Okay, so this one has 18 steps, and I know some of these are kind of hard to see, but this fault here is K, and this one here is X. So again, feel free to pause the video and try it on your own, and then come back and see if you got it correct. Okay, so again, we're going to start at the bottom and see what we think came first. Okay, so one of the important things here that we notice is that there's a piece of F inside of P. So if there's a piece of something inside something else, then it must be older. So here we would surmise that F is probably the oldest here. And then since G cuts through P, G must be younger than P. Okay, so a couple of things here to note. We knew that F was older than P because of the principle of age of inclusions. Okay, so on your lab, you will be asked, based on the order that you put things in, what principle you used. Did you use original horizontality? Did you use superposition? Was it age of inclusions? Was it cross-cutting? So with these, I'll try to go through and make sure we know which ones are which. Okay, so with P, we used age of inclusions and cross-cutting and superposition. So you'll just pick one, whichever one was the most pertinent. Here's probably superposition was one that was most pertinent, and then for F would have been age of inclusions. So then for G, that would be our cross-cutting relationships, okay, because it cross-cuts P, but it does not cross into B. And another thing you notice is that B not only is on top of P, but it also has little pieces of P in it. So then our next layer would be B. Oh, I'm sorry, the unconformity, I missed that one. So we have our unconformity here, a squiggly line, and then we will see B deposited. Then the next little scenario we have is R and M. Well, M cuts through just R. It doesn't cut through H or A or any of these other layers up here. So we know that it is younger than R but it must be older than H. So next we have R, then M, and H, and then finally A is on top of all of those, and then all of those layers are folded. So all the folding has to happen after A is deposited. Okay, and then after A, we have another unconformity here, another squiggly line. Okay, so that's our unconformity L. And then we start to see the deposition of more layers. Note we still have this fault, but if you look, this fault cuts through everything except for J and S. Okay. So our unconformity, that would be a principle that you would write. You would write unconformity and then what type of conformity. You see this one appears to be a disconformity between sedimentary layers. This one down here is a nonconformity between an igneous layer and a sedimentary layer. Okay, so next we have the deposition of E, and then this is an X here, and then our D. And then it's hard to tell whether you have the tilting event or K, but most faults come in at an angle. And if they are at a lower angle here and it was pretty close to the same angle as these beds, then you might say that K came before the tilting event. But in a diagram like this, it's really hard to tell. So we're going to say that the tilting event happened first. And then you have an unconformity. Oop, we forgot K. Whoops, okay. So one thing to note here is that the unconformity does come before K, just because you know that this is a horizontal surface here. This would be a step up here. Remember, dip-slip faults move things up or down, which will have an offset surface. So you wouldn't see this horizontal line here. So the unconformity has to come before K, but that doesn't mean that J is next. So it would be K, and then J, and J is before S because J would have been laterally continuous, and it is not, so that indicates that it came first and then was eroded, and then S was deposited. Okay, so hopefully that one was okay. We're going to do one more and see if you get any better at this. Okay, so here we have a few different steps. There's only 10 here, so it's a little bit more simple. But we also have an erosion layer and a folding layer. And by erosion, this is another unconformity. Okay, so again, start at the bottom. Our bottom layer here is H, so that is likely the oldest. And then our next layer is F. And then on top of F is C. Okay, and then all of these layers are folded, but the ones here towards the top are still horizontal. So you would say that your folding came next. And then your erosion, right, so the squiggly line here. And that unconformity is a disconformity between two sedimentary layers. And then your B here cuts through all of the layers, so we'll get to that last. So next we're going to look at A. And then on top of A is E. On top of E is D. So all three of those layers are the principle of superposition. And then we have some cross-cutting, which would be B. And then we have G. Now, it gets a little bit tricky which one you think comes first. Depending on what you're looking at here, because this is a direct intrusion, it's a little bit hard to say whether B or G came first. If it was a volcano and there's a magma chamber here, of course the magma chamber has to be there before there is any development of the volcano. Either way, on like a lab or an activity, I'll try not to give you anything super ambiguous. I'll kind of accept either one. But for now, similar to the magma chambers situation, we'll say that B had to exist first before G. Okay? So G would be our youngest layer. All right, so this is the first one that we looked at. And let's see if we can do it. It has a lot going on. There are a total of 12 steps, but I think we can do it. Some of the other ones I think were a little more complicated than this one. So again, towards the bottom here, we want to look at what we have. So we have these horizontal layers here. They're offset by a fault. We also have an intrusion here, but this intrusion cuts through quite a few of these layers. So it's not going to be our oldest, even though it's towards the bottom. If it cuts through a layer, remember that layer has to be there before it can cut through it. So that means that G must be our oldest layer based on superposition. Then we see F, then E, and then we see I. So you might say, oh, but I only goes through 2 layers. Yes, but you can't see G's layer on this side because it's truncated at the bottom. The fault has moved this side up and this side down. Okay, so I does cut through E, which is offset here. Okay, so then after that, you would see the deposition of D. And then would you think that Y would come next or X? That one's a little tricky. The key there is that X is offset by the fault as well. So if it's offset by the fault, that means it has to be older than the fault. So X would be next, that erosion feature. And then you have Y offset all of it. Okay. So next we have A, B, and C, and then we have H and J left. Okay. So H cuts through all of these layers. Okay. So our next layer would be C, B, then A, and then H. Just because H doesn't come to the surface doesn't mean that it doesn't influence A. A has to be there in order to do this kind of ridging, wrinkling at the top on the surface. So this pluton is pushing up through the surface and is causing some rippling effects, mountain-looking effects at the top of this diagram here. So this layer would not have been deposited in this manner if the pluton wasn't pushing up on it. Okay, so then last but not least, we have the deposition of J. All right, so that was relative age dating. Now we're working on absolute age dating. So this is using something called radioactive decay. So when rocks are created, they are not always the most stable in the environment for long periods of time. And so different elements will decay over time to what we call daughter products, and that helps the rock become more stable. So this is called radioactivity, and we use the principle of radioactivity to help us radiometrically date rocks and figure out exactly how old they are based on the decay products that we see. So radioactivity is the spontaneous breaking of the atomic nuclei. So we're looking at the nucleus of different elements and watching them basically decay to something else. So the radioactive decay process takes a parent, which is an unstable isotope, and it turns it into a daughter, which is a more stable isotope. So the parent to the daughter. And depending on the unstable atom that you have, or the unstable isotope that you're looking at, you will see a very particular decay product. So for instance, when we have uranium in a granite, it will oftentimes decay to something like lead. Lead is more stable in the environment than uranium is. Now, it takes a long time for this to happen, and depending on the isotope, it'll take different amounts of time. So depending on how much of the decay product you have in a particular sample, that can tell you how long that sample has been sitting there. So then you can get an age from that sample. So radioactive decay can occur a couple of different ways. We can see an alpha emission, a beta emission, or an electron capture. So in the decay or the unstable parent nucleus, in an alpha emission situation, you have the loss of an alpha particle, which is a proton, 2 protons and 2 neutrons, and they are basically ejected from the system, and then you're left with a daughter nucleus, which is a decay product that's much more stable. In a beta emission, this is when the unstable parent isotope releases an it loses an electron. So when it loses an electron, it changes a neutron into a proton, because a neutron is negatively charged. If you lose an electron, then it remains positively charged. So this is beta emission. And then with an electron capture, that's when an outside electron adds to one of the protons in the unstable parent nucleus, and now you have an extra neutron in the more stable daughter nucleus. Okay, so this is the way that we can see radioactive decay from one isotope to another. Okay, and the way that we measure how long it takes for these unstable particles to decay to more stable particles is something called a half-life. And so the half-life is the time it takes for one half of the radioactive nuclei to decay to the more stable daughter product. Okay, this requires a closed system, and we use a lot of different cross-checks to measure the accuracy of our counts. And it's a very complex procedure, but we can yield actual numeric dates from it. We use things like giant mass spectrometers that actually count individual isotopes, which sounds really crazy, and they are very, very small. And there we can actually decipher how old something actually is. We can say definitively, or with a level of uncertainty, that it's 100 million years old, or 11,000 years old. Okay, so with every half-life, you're losing half of the parent isotopes, and they're decaying to daughter products. So you'll notice in this little diagram here that every time a half-life occurs, you start to see more daughter products and less of the parent isotope. Okay, so over time, so these are different half-lives, you'll lose 50% every time. So if we start with 100 parent atoms, after the first half-life, we only have 50 left. After the second half-life, we now only have 25. So you're not taking 50% away from the original, it's 50% each time. So after one half-life, it's 50% of the original, and then after two half-lives, it's 50% of what was left over after the first half-life. So 100 decays to 50 in the first, 50 decays to 25, 25 to 12.5, 12.5 to 6.25, excuse me, 6.25 to 3.125. And this never actually reaches 0 because there is no number that you can divide by 2 or take 50% of and actually get 0. So it asymptotically reaches 0. Okay, so one radiometric dating technique that we use is called carbon-14 dating. This only has a half-life of 5,700 years or so, and this is really good for dating very young things. So looking at bones from very recent fossils, things like mammoths or saber-tooths, carbon-14 is very useful for things like that. Whereas the uranium and lead that I talked about earlier, that's more so for things like plutons, granite, volcanoes, rocks, mostly. For fossils, a lot of times we use carbon-14 dating because most fossils have some sort of carbon element to them. So instead of saying that the Somerville Foundation is the oldest and the Wasatch Formation is the youngest, and that this igneous dike is younger than these 3 layers here, but older than this layer, we can actually definitively say with radiometric dating, with absolute age dating, that this dike is 66 million years old. Okay. All right, so we're going to work on some problems now. I'm going to switch to the iPad, so you can come back to this section if you need to reference it. So we're going to go through these 3 questions, and I'm going to write it out for you so you can actually see it. So the first question is, you have 500 atoms of radon-222, and after 8 days, how many parent atoms are left? So here you'll note there is a table down here for you to use. So for radon-222, the half-life is 4 days. So then you have to figure out how many half-lives it's been through, and then we'll do the calculation on that. Number 2 says, suppose there are 1,000 atoms of plutonium-239. After 72,360 years, how many parent atoms are left? How many daughter atoms are produced? So there we're going to do a 2-step. And then number 3, suppose a particular sample has 25 parent atoms and 375 daughter atoms. How many half-lives has this sample experienced? How many parent atoms were originally in the sample? Okay, so now we're going to do all of them on the iPad, and then you'll be able to see exactly how to do these. Okay, so we're going to work on the problems in the PowerPoint. So we're going to start off with number 1, which says that we have 500 atoms of radon-222. Okay, so this has been decaying for 8 days. So we'll write down 8 days. That's an important number to remember. And then the half-life of radon-222, if you reference the table, is 4 days. So in order to lose half of the parent atoms, it takes 4 days for that to occur. So you're going to want to figure out how many times 4 goes into 8. And that would be 2. So here we need to take the original parent atoms and we need to cut that in half for however many half-lives have occurred. So we do this step by step. So we start with our 500 atoms. And like I said, we have 8 days of decay. And the decay of radon-222 by half is 4 days. So that means we need to go through 2 half-lives. So we'll take the 500 atoms and we'll divide by 2. So that'll be our first half-life. And 500 divided by 2 is 250. So we write that down. And then we need to divide by 2 one more time. We need to cut it in half again because it's gone through an additional half-life, not just one. So if you want, you can write down this is our first half-life. Okay, divided by 2 again. We're going to run through our second one. So 250 divided by 2 is 125 atoms. And because we are only going through 2 half-lives, this is our answer. Okay, so we have 125 parent atoms left after 2 half-lives of radon-222. Okay, and the next step, if you were asked about how many daughter atoms were left, you need to find how many are left from the 500 we originally had. So you'll take 500 and minus 125, so you'll get 375 daughter products. So daughter atoms are what is decayed after the parent goes through a half-life. So we now have 375. And these two numbers here have to equal the original amount of atoms we had in the sample. There is no loss of atoms in the system. Okay, so we're not losing atoms. Our parent atoms are simply decaying to daughter products. So your daughter and your parent atom answers need to equal the original. Okay, so let's move on to number 2. So number 2 says that we have 1,000 atoms of plutonium-239. Okay, and plutonium-239 has a much longer half-life. And this sample has gone through 72,360 years of decay. And if you look at the table, plutonium-239 has a half-life of 24,120 years. So when you work on these problems, you want to make sure that you're writing down all of these numbers so that you can have them for easy reference. Okay. So, how many times does 24,120 go into 72,360? If you need, you can use your calculator for some of these. You can try to do it by using your math skills in your head. Not all of us are that impressive, but it's gone through 3 half-lives. Okay, so 72,000 divided by 24,000 is about 3. So 3 half-lives. So we take 1,000 divided by 2, so that's 1 half-life. That gives us 500. Divided by 2 one more time. That gives us our 250. So that's our second half-life. One more time. That's 125 atoms. So by our third half-life, see we've done it 1, 2, 3 times. We're left with 125 parent atoms. Okay. So then this question also asks how many daughter atoms were produced. So again, here we're just going to take our original 1,000 atoms and we're going to subtract the number of parent atoms we calculated, so 125, and we are left with 875 atoms. So we'll write that down, 875, and those are our daughter atoms. Okay, and again, you'll notice that these two numbers 875 and 125 equal 1,000. All right, so moving on to number 3. Here, our question is a little bit different. We are looking at a sample that has already gone through half-lives. So we have 25 parent atoms left and 375 daughter atoms left. We're asked to figure out how many half-lives it's gone through and how many parent atoms were originally in the sample. So the first question to answer is the original parent atoms question, because that'll tell us how many atoms to start with before we figure out how many half-lives it's gone through. So again, there's no loss of atoms here. So we are given 25 parent and 375 daughter atoms. So we'll write that down as well. Since there's no loss of parent atoms, all we're going to do is add them together. Okay, sorry about that. Okay, so we're going to take our 375 and add that to our 25. So 375 plus 25, that gives us 400 parent atoms. Okay, so those are our original atoms in the sample. Now we can go through and divide by 2 a few times to figure out how many half-lives it's gone through to end up with 375 daughter and 25 parent. So we'll take 400, divide by 2, it's 200. Divide by 2, that's 100, divide by 2. Here we're looking for 25 again, okay? And there it is. So we've gone through 1, 2, 3, 4 half-lives to end up with 25 parent. Okay, so there they are for you. Okay, so we had to divide by 2 4 times to get whatever we were given, the 25 parent atoms. So this is 4 half-lives, and the original atoms in the sample, or the original parent atoms, were 400. Okay, so hopefully this helped you guys out, and I hope to see you guys in the next one.